So in problem 3, we want to perform a hypothesis test here. We're looking at the tensile strength or the breaking strength of two synthetic rope materials. They're both 3/8 inch diameter size. That's actually extraneous information. And our results here are given in thousands of pounds. So for the first material, the breaking strength of the first sample was 5.1 thousand pounds, so 5,100 pounds, then 4,300 pounds, 4,800 pounds, and so on. So notice that there are 6 data values here, so N1 is actually equal to 6. And then for the second material, there's 9 data values, tensile strength in thousands of pounds again, so N2 is equal to 9. The question we're asking is, can you conclude that the standard deviation of the tensile strength of material 2 is different? So different from material 1. Use the alpha is 0.10 level of significance. We'll notice here that we are assuming that the dot plots are approximately normal with no outliers. Those are the test requirements. So that's given to us. We don't need to check that. First thing we need to do is state our appropriate null and alternative hypothesis. The alternative is what you're trying to show. So we're trying to conclude that the tensile strength of material 2, that standard deviation on, is different. So that's going to be our alternative hypothesis, is that the two standard deviations are different. So that would be sigma 1 not equal to sigma 2. And then if that's not the case, the default hypothesis is that sigma 1 equals sigma 2. So the standard deviations are the same. Is this a left-tailed, right-tailed, or two-tailed test? Not equal is going to be a two-tailed test. So next we want to go ahead and find our critical values. Now when you're testing two standard deviations, that uses the F distribution, which is similar in shape to the chi-squared distribution, but it's more skewed, more pronounced skew in it. So this distribution looks something like this. And then part B, they want us to find the critical values, round to 2 decimal places. So the way that our test statistic is set up, you only have one decision rule, whether it's lower-tailed or upper-tailed, that is whether it's left or right-tailed, you have the same decision rule. So you need to find your critical value. So for us, that's going to be F alpha over 2 because it's two-tailed. So there's going to be an F alpha over 2 here. And their notation is to use a lowercase f for the critical value and an uppercase for the test statistic in the name of the distribution. And this is a two-tailed test. Our alpha is 0.10, so alpha over 2 here is 0.05, and that's the area of the tail. So this area here is 0.05. And that's the area of the rejection region. The rejection region is the area that's past the critical value. So we're going to find the test statistic. If it's out here, we're going to reject H0. Now you might be looking at this and saying, well, wait a minute, this is a two-tailed test. Well, why don't we have 2 rejection regions? And the reason is because of the way that we've set up the test statistic. The test statistic is the larger of the 2 variances on top divided by the smaller of the 2 variances on the bottom. So this could actually be, 2 different possibilities, either S1 squared on top and S2 squared on the bottom, or vice versa. So since they set it up this way, you always just have a right-tailed picture, even though it's two-tailed. So what is our critical value here? Well, we're going to use the Excel distribution calculator. You can also use the text. I think it's easier to use the calculator though. So you open the distribution calculator. You want to go to the inverse F distribution tab. And then we need to fill in alpha over 2, which that's already set for us, 0.05. And then our numerator degrees of freedom and our denominator degrees of freedom. And then here's going to be our critical value. So numerator and denominator, in order to do that, we need to know which one goes in the numerator and which in the denominator of the test statistic. So we need to find out which variance here is going to be on top, which one's the larger and which one's the smaller. So let's put these into the TI-84 and find our two standard deviations, and then we'll square them to get the variances. So there's the calculator. You want to go to Stat and then Edit. And now I've actually already entered the data in here to list 1 and list 2. And so we want to go ahead and find the first standard deviation. To do that, you're going to go to Stat and then Calc. And we want one variable stats. And then we're going to do list 1 first. List 1 is for the first sample here. So I'm going to do second function of 1. And see this changes to list 1. We're going to arrow down and calculate. And S sub x right there, 0.3448. That is S1. And then we want to do the same thing for, 3488. And then do the same thing for S2. So again, we're going to go to Stat and then Calc and one variable stats. But now we want to do list 2. So we're going to do the second function of 2. That puts list 2 in there. Highlight, calculate, enter. And now our standard deviation is 8115. So 0.8115. And then if you square that 0.3488, you'll get 0.1217. If you square the 8115, you'll get 0.6585. So S2 is the larger variance and S1 is the smaller. So the larger goes on the top, that's going to be the S2 squared. The smaller goes on the bottom, that's going to be the S1 squared. So our numerator degrees of freedom is going to go with S2. Our denominator degrees of freedom goes with S1. So for S2, our sample size is 9. For S1, our sample size is 6. So this is numerator, and this one is denominator. So go back to our distribution calculator, and our numerator sample size is 9. 9 minus 1 is 8 is our degrees of freedom. And then our denominator sample size is 6. 6 minus 1 here is going to be 5 degrees of freedom. And 4.818, so 4.82 will be our critical value. So this is 4.82, and this is 4.82. So for two-tailed, you're going to take alpha and divide it in 2. Okay, and that shows up right here. So that's alpha over 2, right? Areas of decimal, divide alpha by 2 for two-tailed tests. Okay, so now we want to compute our test statistic. So let's go ahead and finish that computation. And so the larger of S1 and S2 squared is the 0.6585 up on top. And the smaller of S1 and S2 squared is S1 squared, which is 0.1217 in the denominator. And then we want to go ahead and divide those. If you divide those on the calculator, you will get 5.41. So here's 4.82 is right here, and then the 5.41 would be right here. And you can see that that is indeed in the rejection region. So we're going to reject the null hypothesis here. So our F test is 5.41. That is greater than 4.82, which is our F.05. And so we are going to reject H0 because our test statistic is in the rejection region. So then we state our conclusion is going to be that there is enough evidence to conclude that the standard deviation of the tensile strength for material 2 is different than that of material 1.